Now let's look at our goal. Yeah, so let me clarify our current goal. Yeah. The highest goal, that is, we want to find the best approximation. Yeah. The infinite series, because we can only use the finite number of terms in the real world calculation. Yeah. So we consider the general trigonometric polynomials of degree capital N. All right. Yeah. And here, because we have a special trigonometric polynomial of degree N, that is the partial sum of the Fourier series. Partial sum. Yeah. Now we want to show here, yeah, because in our mind, we should have some target, yeah, in our mind. So our target is we want to show when the capital A, capital B coefficients equal the little a, little b coefficients, we will get the best approximation. Best approximation means the error term in our square of error definition, that definition, okay? Yeah. Our error term is the smallest. Okay? All right. Here we have the general error expression, capital E. That's the general error expression. Special error expression, E star, the special error expression. And we want to show capital E is greater or equal to capital E star. Yeah. So here, our goal. Yeah. So we need to have some target in our mind. Yeah. Yeah. Otherwise, so we cannot go to the next step. Okay? All right. So the current goal, oh, I need to change my pen color. All right. So the current goal becomes we want to show capital E always greater or equal to capital E star. Okay? All right? Yeah. Then we get minimum error. Right? Yeah. All right. Minimum square error. You have this. All right. All right. Yeah. So let's do subtraction. Right? Yeah. Because when we do that, yeah. Let's do subtraction. We want to show capital E minus capital E star greater or equal to 0. Yeah. When we do subtraction, the first integral term is gone, right? Cancel out. Yeah. We do not need to worry about. Yeah. Otherwise, it's not easy to calculate f squared, right? Yeah. It's not easy to calculate f squared integral. Yeah. Right? Yeah, but when we compare the errors, we can get around it. We do not need to calculate the integral. Cancel out. Okay? All right. Yeah. So now let's compare the remaining terms. Subtraction. Yeah. So here, all right. Yeah. So let me erase that part. The main formula. So here I show you. Other than this, the main formula. The difference, E, capital E minus capital E star, the difference, yeah, we can get a complete squares, yeah, because so you group them carefully, okay, yeah. So I think it's not hard to see this, yeah, because, yeah, all right. Let us consider one particular term, all right? Yeah. Yeah. All right. You have a little a n square, all right, minus capital AN, little an, right? 2 times capital AN, little an. Yeah, so I need this. Yeah. Plus n square, right? Yeah. So, one typical, complete square. That equals little a0 minus capital A and 0 square. Okay? Yeah, so that's this part. Yeah. For other squares, you can do similar things. Yeah. So you group the terms carefully. Yeah. Group the terms. So here, I did a typical one here. Okay? Typical complete square. Yeah. So other parts, you can get similar things. So you will get, and you can see in this square representation, it's non-negative, right? Yeah. Because each term is non-negative, greater or equal to 0. Yeah. So it tells us, this E star, this special case, really gives us the minimum square error. When you use the Fourier series coefficients to write your trigonometric polynomial of degree n, the partial sum way, use the partial sum way to write it, you will get the best approximation in the sense of minimum square error. Yeah. That's important. Yeah? Yeah. That's the meaning of this theorem, minimum square error theorem. Yeah. All right. So let's look at the all right, yeah. Yeah, theorem part. Okay, all right. Square error of f into, yeah. So we know the error definition, right? Yeah, so in this interval is minimum if and only if the coefficients of f into, are the Fourier coefficients. Yeah. So 2, whatever, yeah. So we mean the form should be here. Yeah. Oh, sorry. Yeah. Yeah. Coefficients. This minimum value E star is, the equation number, but we know the, yeah. So here, let me erase this part because it's covered this. Anyway, yeah. All right. Yeah. All right. Yeah. So this minimum square theorem. All right. Yeah. Now in our real world calculation, it's very easy. Given little f function, when you want to do approximation, the best way is use the Fourier series expansion, and you take this first few number of terms, you calculate the partial sum. You use the partial sum to approximate original function, and in the sense of minimum square error, you get the best approximation. All right. Yeah. All right. Bessel's inequality and the possible identity. Yeah. Now we want to understand more. Yeah. In the previous slide. Yeah. So let me go back to the previous slide. All right. Remember, in our calculation here, this part. Yeah. So here I cross out this integral, this part. We get around it. Yeah. So we didn't calculate it. Yeah. Now we want to calculate this square integral. Okay? In terms of the Fourier coefficients. Yeah. So we want to see how to calculate this integral in terms of the Fourier coefficients. All right. Yeah. Bessel's inequality and the Parsifal's identity. Yeah. So this result, we get another important property. All right. Yeah. So let's look at E star. Yeah. All right. This E star is non-negative, right? Can you see E star non-negative? Because square integral, right? Integral of difference, square of difference, right? That must be non-negative. Yeah, so we know the definition here. That is the f original function minus this time partial sum, right? Yeah, yeah, because we use partial sum, capital Sm. Yeah, remember our old notation for partial sum, S sub n, right? Yeah, partial sum square. Yeah, so this E star equals this function square, right? So it must be non greater or equal to 0. Yeah. Integral of square cannot be negative, right? Yeah. All right. Then, from this simple observation, we can get a simple inequality. Yeah. This simple inequality, that is, yeah, this, yeah. So this cycle equal, we do some simple algebraic operation, we get this inequality. That's the Bessel's inequality. Okay? Bessel's inequality. Yeah. From the error, Bessel's inequality. Okay? Yeah. All right. Yeah. Then, next, we need to look at a possible identity. Starting from Bessel's inequality, closely related, then we get to the possible identity. All right. Yeah. So this Bessel's inequality, we only use n terms, right? Yeah. So n, capital N, degree capital N. How about we increase this capital N number? We use more and more degree number, higher and higher degree N number. Okay, yeah. The higher, so because we have more and more terms, right? More and more terms. Yeah. We have the inequality, but the difference of left-hand side and right-hand side becomes smaller and smaller, right? Yeah. The difference becomes smaller and smaller. Yeah. Now the question is, when we make capital N goes to infinity, capital N goes to infinity, what will we get? Will we get an identity or still inequality? Yeah. Because when we make N goes to infinity, we still have the inequality. But the question is, can we make this inequality to identity? That's the question. Yeah. Because we don't know. If it is identity, we know it must be an inequality, but we don't know if it is an identity. Yeah. To show it is an identity, we need to prove it. We need to prove it is an identity. So that's the possible identity. Okay, so we need to do some math work. Yeah. All right. Yeah, so the Bessel's inequality. Yeah. All right. Oh yeah. Bessel's inequality, even infinity, yeah. Other than that, even infinity, we have this. Yeah, that's Bessel's inequality. But actually, this can be identity. So here you can see the Parsifal's identity actually is stronger than the Bessel's inequality. Yeah, because this Bessel, this guy at that time, he could not prove actually this is an identity, not less than equal. Yeah. So the Parseval later improved this result. Yeah. Make it equal. Yeah. So there is no less than case. Yeah. Yeah. All right. Yeah. So here, so we try to prove. Yeah. All right. Yeah. So this trigonometric, remember the last time I talked about this trigonometric system, there is a special property called completeness. This trigonometric system, in this way, it is a complete system. Complete system, what's the meaning of complete? Yeah. That means, so remember last time I mentioned there is a term, in engineering, the term, this integral, so people call it energy. Okay, energy. Yeah. All right. Yeah. What? I cannot control. I cannot control here. Yeah. Yeah. Whatever. Yeah. 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 So this is the energy. Yeah. All right. Then, because each term here, left-hand side, we only pick up a part of the energy, right? So when we use capital N, this many terms, certain number of terms, we get a part of the energy, right? We pick up part of the energy. Yeah. So then we increase this capital N number so we can pick up more and more energy, right? Yeah. We try to recover, all the energy that comes from the original function. Yeah. Here the question is, when this n goes to infinity, can we pick up all the energy without any loss? No loss. Okay? Yeah. Yeah. So here, this trigonometric system, completeness, it is complete, tell us, yes, we can. Yeah, because complete means nothing is missed, right? Yeah. Yeah. Energy means useful information. So we can pick up recover all the useful informations without any loss. Yeah. So this whole system is complete. No energy loss. Okay? Yeah. All right. So that's the meaning. Yeah. Yeah. So there is this possible identity. Yeah. It can be proved. Okay? Yeah. So probably here I skip the proof because this is not a math class. Yeah. I just tell you the result. Yeah. Yeah. So some of the proofs you can find in our textbook. Yeah. Yeah. I skip. Yeah. All right. D.2, minimum square error for the sawtooth wave. Yeah. So special shape of the wave, tooth, saw. Okay, saw. The tooth of the saw, of a saw. Right. So let's calculate. Yeah. This is the sawtooth wave. Yeah. So we want to, use the partial sum to approximate this function, and look at its error. All right. So define the sawtooth function x plus pi in the interval between negative pi and pi. Yeah. Then we do 2 pi periodic extension. All right. Then we find the Fourier series of the sawtooth function. Yeah? Yeah. Because here, it's not an even function and it's not an odd function, right? Yeah. So here, it's not even function, not an odd function. So we need to use the general case formula to calculate the Fourier series. Yeah. All right. Yeah, but here, although it's, actually, so here there is some nice little technique we can apply here. Yeah. Although the original function is not even odd, But we can split the function. The f function equals f1 plus f2. Yeah, x plus pi. Yeah, two functions. Yeah. Pi constant, right? Yeah, constant. Constant is an even function. f2 constant pi. It's an even function. And x, it's an odd function, right? Yeah, odd function, even function. Yeah, so we can split. Yeah, f1, f2, odd function, even function. Yeah, so we can calculate them separately, right? Yeah, so here, yeah, yeah. So let's calculate them separately. Yeah, sum and scalar multiple. Yeah, because Fourier coefficients of a sum, f1 plus f2, are the sum of the corresponding Fourier coefficients of f1 and f2. Yeah. 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 So we use this property. Yeah. The linearity property, right? It's like a linearity property. Yeah. Yeah. So very convenient. Yeah. So with this property, although for this special example it looks very simple, but for some other examples, if you can observe this special property, yeah, yeah, for some other relatively hard examples, you will see. If you split, then your calculation much easier. If you put them together, although you can also calculate, yeah, but the calculation much harder. Yeah. All right. Yeah. Yeah. So here, let's use this property. Yeah. Yeah. Oh, so here, another thing is f2, we do not need to do expansion. Because this single term, it is already a Fourier series, right? Can we treat it like that? Yeah. Because in our Fourier series, we added this pi on top of a0. How about that? Fourier series expansion. That pi is a constant. Can we add this pi on top of a0, the constant term? Yeah. That's even much easier. Yeah. So for this part, yeah. So we can leave it out. So we calculate f1. After that, we apply this property, add them up. Yeah, we get a final answer. Yeah. All right. Yeah. So it's an odd function. So we can calculate using the Fourier sine series. Yeah. Yeah. So here, let's do the calculation here. Okay, all right. Only the x part, only this part. Yeah. All right. Apply the formula b and yeah. So that's yeah. So then after that, yeah, the answer. Yeah. So we can write this f1 Fourier series expansion. Yeah, it's a Fourier sine series formula. Yeah. Then f2 on top of this constant term, right? Yeah. Add another pi on top. Yeah, we do not need to do other terms. Yeah. All right. But here we like to, yeah. So here we already added this pi, right? Yeah. Because f1 we do not have this pi term. Think about it. Yeah. f1 we only have the sine terms. Yeah. So we don't have other terms, right? Yeah. So for little fx, here we already add this constant pi there. Now we want to look at the approximation, the error term, E star. Yeah. All right. Yeah. So because here we can calculate the f squared. Yeah. Little f function is very simple. Yeah. So we can calculate directly. Yeah. All right. Yeah. Oh, do we have? Yeah. So we draw graph, right? We calculate error term like that. Yeah. Approximation like that. Okay? Yeah. Yeah. All right. Yeah. All right. And when n goes to capital N goes to infinity, yeah. So you can see the the error part becomes smaller and smaller. Yeah. E star goes to 0. Yeah. All right. Yeah. So by the Parsifal's identity, here we want to verify. Yeah. So Parsifal identity in the previous slide, because this little f function very simple, so we want to verify it. Okay, yeah. Verify, yeah. 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 All right. Yeah. Yeah. Actually, so here we do not verify it. Yeah, because verify is non-trivial, right? Here we just want to apply Parsifal's identity to get another identity. To get this. Yeah. After cancellation, simplification, we get another identity, right? So we get this identity. Yeah. So here we have another way to show identity from Parsifal's identity. Yeah. We can show that. Yeah. Yeah. In our part C, we use the Fourier series expansion to show some identity, right? Yeah, based on the convergence. Yeah. Based on our convergence theorem. Yeah. We have one way to show identity. So in this part D, we can apply Parsifal's identity to show this kind of identity. Yeah. Pi related. Yeah, many times it's pi related. Yeah. All right. Yeah. So that's the next. Yeah. From Fourier series to Fourier integral. Yeah. Another important improvement. Yeah. So Fourier series, something still not good enough. We want to improve. Yeah. So the way to improve it, introduce Fourier integral. Yeah. So let's look at extend Fourier series to Fourier integrals. Yeah. All right. Fourier series is a powerful tool, but with limitations. Yeah. All right. The first one is when we work on non-periodic function, then we cannot use Fourier series. Fourier series, little f function must be a periodic function. Sine, cosine. The modeling function, sine, cosine, periodic. Yeah. But in the real world, most of the functions are non-periodic functions. No. Periodic function, relatively small portion. No. The most part, non-periodic. No. So Fourier series is not good enough as a representation for non-periodic function. Yeah. All right. And the domain is the whole axis. Yeah. So here, the second case, domain whole axis. Yeah. So what's the meaning? All right. So here, when we consider the non-periodic function, but the domain, if the domain is not whole axis, yeah. So let's look at a special case. Suppose we have a non-periodic function from interval a and from little a to little b in this interval. Okay, yeah. Non-periodic. Okay, yeah. If it's not a whole axis, in an interval, can we do periodic extension? Yeah. Another interval, we do extension. Copy. Okay. Yeah. We do periodic extension. Yeah. Periodic extension. We can still use the Fourier series. We can still use the Fourier series. Okay. Yeah. Yeah. Non-periodic, but only in an interval. The function given, only defined in an interval. Okay? All right. But the second case, non-periodic, but the domain is the whole x-axis. You cannot do extension, right? You have to accept it as is, right? You have to accept the given function as is. You have no chance to do periodic extension because the given function already covers the whole axis, whole x-axis. No way to do periodic extension, right? You cannot modify the function. You have to take it. In this situation, the Fourier series method doesn't work. So we have to we have to extend it, yeah, although it doesn't work, but we can extend it to make it work. Okay? To make it work, the integral must be applied on the whole x-axis. Yeah. So here, let's look at the conversion part. How to extend it? Yeah. All right. Yeah. All right. Yeah. So we consider the general Fourier series expression. All right. All right. Then here we use the because this general formula is applied on periodic function, right? Yeah. So now we take the integral, but when we take the integral, so here, so this part, so we connect all the periods, so the function, all the periods, but when you connect, you need to find a smart way to connect them, to put them together, because our goal, we want to cover the whole axis, all right, and when we connect, so here you can see the cosine, the sine, use this way to connect, because we need to find a way when we put them together, it is convergent, right? We cannot use the arbitrary way to connect them. We have to use some, the way is reasonable in structure. So here, so this way, all right. Then, so let's look at what will we get. Okay, all right. So we will get double integral. Yeah, you can see the double integral. This double integral, there are two parts. The first part related to the cosine, the second part of the sine. They're quite symmetric. So sometimes in math, so when we work on formulas, all right, so try to show some nice property. So when you get the structure symmetric, the symmetric structure is very common. The right way, usually is a symmetric way. All right. So here, so we have this. But in this way, when we represent this way, we want to introduce a capital A function. It's an integral. So this part, we want to use one function, special function, so we call capital A function, and a capital B function. So here you can see, the integral. And when we calculate capital A function, capital B function, here, you can see, we do not require little f function periodic, right? So here, you can see, when we make this kind of connections, so here I want to, make sure that, so this part, because this part, when you see it, it's like a magic, right? How you come up with this special formula? It's like a magic. All right. So then, this part actually, we just want to, when we do the logic thinking, we just want to follow some path, something that guides us, something that guides us to some reasonable formula, things like that. So our goal, we want to derive this formula, because we have to have some base, right? We have to have some, reasonable path to get there. Yeah. So we cannot just, suddenly we find a magical way, right? Yeah. So that's not realistic. Yeah. So this part, yeah. So basically, so people just try to get some inspiration, things like that. Some inspiration, yeah. Something, yeah, reasonable, yeah, but may not be rigorous math, yeah. So this part, is for the inspiration part. May not be rigorous math, yeah, because people may ask, why you do this, why you do that. So here it's a periodic function, but when you get here, it's a non-periodic function, right? So that kind of argument may not be very rigorous in math, yeah. But people just use that kind of thing to, get inspiration, to get something useful. At the end, this formula is useful, okay? This formula is useful. But you need to derive the formula through some logic reasoning, right? Yeah. It cannot come from nothing. So that nice formula cannot come from nothing. Yeah. So you need to do some reasonable, logical thinking. Yeah. Yeah. So this part, yeah. So do not ask too many questions. Yeah. Yeah. So that part is not very rigorous. Okay. Related. Yeah. It is closely related, but may not be very rigorous. Yeah. Yeah. All right. Yeah. So now at the end, yeah. So the final formula, very useful, very important. Yeah, it's correct. Final formula, because we can prove it, right? So here you can see this part helps us to guess the right formula. Okay? Yeah. Yeah. Because many times people need to guess the formula. Guess this formula. But the way you make a guess, you don't want to do baseless guess, right? Yeah. You guess from nothing. That's a baseless guess. So you need to have some reasonable base, right? This is the reasonable base. Yeah. So you have something reasonable to start with. Okay? Yeah. Yeah. But the way you try to look for the right formula, yeah, sometimes some of the steps may not be very rigorous. Yeah. Many mathematicians did a new discovery in this way. Yeah, Euler did a lot of discovery like this. Yeah, yeah, because in a lot of calculation that Euler did, so non-convergent. Yeah, yeah, he just did it. Yeah, did it because use that for a guess for the final formula. Final formula we can use different way to prove, right? After you have a nice guess, we can use other rigorous method to prove. Yeah, but to discover this important formula, so you need to do some math work, right? Yeah, but that math work may not be rigorous. Yeah, many mathematicians did things like that. Yeah, not rigorous. Yeah, yeah, yeah. Here we have the similar situation. Yeah. All right. So then, this final formula, now we want to look at the meaning of that. Yeah, all right? Yeah. So when we start, we have given little f function. That little f function, we do not require periodic function. Yeah. All right. Now, we want to represent that little f function, yeah, in terms of a special integral. Yeah, special integral. This time we do not use the series way to represent. Series way, it's a summation, right? Series is summation. Summation and the integral correlated, right? Integral, do we treat integral as a special form of summation? Integral. Yeah? Yeah. Integral, actually, it's a more general form of summation. Integral. Okay? Yeah. Because integral, we can divide it into pieces. We add up those pieces, it's a summation, right? Yeah. So integral, people treat it as a special form of summation. Yeah. So this time, we do not use series to represent our original function. We use an integral to represent. Yeah? All right? Actually, it's more general than the summation form. Okay? Yeah. So the integral. But when we use the integral, we need to calculate, something. Yeah. So this here, capital A function, we calculate it. Yeah. Capital B function, so we have that V. Then we have the integral representation. Okay? All right. So now our final result. Yeah. Yeah. So here, the final result is this formula. Yeah? Yeah. This formula. Okay? Yeah. Integral, yeah. So capital A function. We can calculate it, right? Like a coefficient. We calculate the coefficient. Yeah. But here it's a capital A function. Yeah. Capital A function you can understand. So it covers many coefficients. Yeah. Put many coefficients together using an integral. Yeah. It plays a role of coefficient. Yeah. Then capital B function. So then that's your special representation. Yeah. So this representation, little f, could be non-periodic function. Okay, all right. Yeah. All right, yeah. So, yeah. So let me see. Next topic, if it's a lot of things, so then I need to leave next time. Deliveries discontinuous factor. Yeah. So, what's that? What do we want to do? Representation. Okay. All right. Integral. Yeah. Yeah. Let's leave that topic next time.